In this video we shall continue discussing dependency theory. Please refer to the previous video for dependencies for low-level normal forms, and we shall now discuss dependencies for high-level normal forms. But before we begin, we have to emphasize with such a sad face that all this material is really extremely hard to comprehend. So you may want to review this video several times or read some books. The fourth normal form is based on multivalued dependency that may be written like this or like this. And that dependency states that, first of all, we have to have a relation with at least 3 attributes or set of attributes. And if that relation has 2 tuples with the same value of 1 attribute, it has to have 2 more tuples with cross combination of 2 other attribute values. Yes, it's hard, but we shall now review an example that maybe somehow will be simpler. Let's start with graphical interpretation. These 2 tuples existed initially. Here it is, here it is. But existence of these tuples is defined by multivalued dependency. Why is that? Because we see that these values are the same, so these 4 values should be cross-combinated. Here is an explanation. Of course, it would be maybe simpler to create this relation like this, but we have the first normal form that disallows such situation. We shall talk about normal forms in the next videos. This is how it looks with data. We know that one applicant may apply to several faculties in some university, and one faculty has several entrance exams in the same university. So here's our data. And for each applicant, we have to add as many rows, as many exams there are on a faculty this applicant applies to. So if Sidorov enters physics faculty and we know that physics faculty has 2 exams, we have to add this row to comply with this rule about 2 exams on physics faculty. And let's state that in real life you'll almost never see such a situation, because one has to be rather stupid to create something like that. That's really bad. Just like functional dependency, multivalued dependency may be either trivial or non-trivial. With trivial case, we have the same situation. We have 2 sets, X and subset Y. With non-trivial dependency, we have different subsets, X and Y, and we shall now see some examples. We've already seen non-trivial graphical representation, so please rewind the video a couple slides back, and here are cases for trivial multivalued dependency. The case number 1. Here we have X and Y sets, and we see that this is X and this is Y, and Y is subset of X, so this is trivial. The next situation, number 2, we have set X and set Y. The X is number 1, the Y is number 2, but we remember we have to have some set number 3. No such set here, so once again this is trivial multivalued dependency. And the third case, there may be functional dependency between Y and Z. That functional dependency forces the following rules. For Y1 there is Z1, for Y2 there is Z2, and there may no be a situation when for Y1 there is Z2. It should be 1. And for Y2 there may no be Z1. It should be 2. So these tuples may not exist in such a relation due to this functional dependency. And once again, this is trivial case. The fifth normal form is based on joint dependency. Such dependency states that a relation has to comply with the rule. With any data inside the relation, there should be possibility of lossless decomposition of this relation into several projections. And joint dependency may be trivial and non-trivial. With trivial joint dependency, at least one of those projections contains all relation attributes as it is equal to the initial relation. With non-trivial joint dependency, none of that projections contain all relational attributes, so none of those projections are equal to the initial relation. Let's start with a simple example. This is a relation describing some elective courses, and we see several functional dependencies here. For instance, group identifier depends on lesson ID, tutor depends on lesson ID, topic depends on lesson ID, so here are functional dependencies. And we have join dependency here. We can decompose the initial relation into 3 projections, and then we may use join operation to produce initial relation based on that projections. This is the example of join dependency, rather simple example. The next example is not so simple. We have no functional dependencies here, but we have a join dependency like this, coming from that rule. If a tutor delivers some subject S and some faculty F has that subject S, and this tutor works on this faculty, he has to deliver the subject S on this faculty F. I know it's difficult, I know it's complex. You may almost never see something like that in real life. But let's look at the data. We see that there is mathematics at exact sciences faculty, tuple 1. Here it is, mathematics, exact sciences. We see that Petrov works on that faculty. This is 5, Petrov, exact sciences. We see that Petrov delivers mathematics, number 3. Petrov delivers mathematics. So, Petrov has to deliver mathematics on exact sciences faculty. So, the 6th tuple. This is where it comes from the subject matter and subject matter only. And here is where the 7th tuple came from. There is mathematics on natural science faculty, number 3, mathematics, natural science, yes. Ivanov works on natural science faculty, number 2, Ivanov, natural science, yes. Ivanov delivers mathematics, number 1, Ivanov, mathematics, so Ivanov has to deliver mathematics on natural science faculty. Here is our 7th tuple. Once again, subject matter is the one to blame. So here we may take this initial relation and decompose it to 3 new relations. Then we may use join operation and produce initial relation based on these projections. But imagine that there is no join dependency. That rule about interconnection between tutors, subjects and faculties no longer exists. So, if we try to decompose this new relation, see there is no that 6th and 7th tuples here, we get such projections, and you may easily check that yourself, that no matter how can we join these 3 projections into initial relation, we will never get that initial relation in the same form. We shall get those 6th and 7th tuples that should not exist here, due to absence of that rule interconnecting tutors, subjects and faculties. So here is no join dependency. Dependencies for domain key normal form are simple. Domain dependency states that if we have some value, that value should be of a range or of some predefined set. The set is easier to understand, or maybe it's a range of some values. And key dependency only states that every key value should be unique. This is how domain dependency looks like with data. We have several events, here we have date and day of week, and we have days of week here. So domain dependency holds because all these are days of week. But here domain dependency is violated because a grapefruit is obviously not a day of week. So that grapefruit value doesn't belong to the set of days of week. The key dependency is even more simple. Here key dependency holds. We have unique values for key field. Here we have duplications for a key field. So the key dependency is violated in this case. And now we have the most complex case, dependencies for the 6th normal form. This is generalized joint dependency. It is useless to try to explain this definition, so we shall look at several samples right now. But there are two more definitions about horizontal decomposition and vertical decomposition, and they are also easier to understand by examples. Let's look at those examples. The sixth normal form and joint dependency are dealing with temporal data, a data that contains some date or time. Here's an example. And we may see that during some education path, some student was moving from one group to another and from one faculty to another, and periods for that movements are somehow overlapped. So we may vertically, it as like this, decompose that initial relation into two projections. Here we have only information about faculties, here we have only information about groups. And it's impossible to decompose these projections further vertically. But we may decompose them somehow in other way. It is not vertically but horizontally. Let's see an example. Imagine that some period is not finished yet. It is we have now value here. So we have some periods with start and end, and some period with start only without ending. So these we may take here and this we may take here. So here are our projections, the during projection and the now projection. And yes, this is the ultimate possible decomposition. We cannot do anything with these relations any further. The same approach we may apply to groups. Once again, we have several periods with start and end, so we take them here, and we have one period with start without end. We take it here, once again during now, and that's also the ultimate possible decomposition ever. And please remember that of course dependency theory is much wider, deeper and complex than we've covered in our videos, so please refer to these or any other good books for more information. And in the next videos we shall discuss normalization requirements and at last normal forms themselves.